Okay, this is breakpoint 5, topic 2, and we are going over electrolytic cells. So let's get into it. So, electrolytic cells are non-spontaneous redox reactions that will always result in a negative E cell. So, our galvanic cells will always have a positive E cell, but our electrolytic cells are non-spontaneous, which means they have a negative E cell and a positive delta G, and we'll look more at that when we get into thermodynamics. But this means that it requires a source of energy, so a direct electrical current in this case, hooked up to two electrodes. And in the diagram down below, we'll see our electrodes look a little different than in galvanic cells. They're in the same solution, they're immersed in a molten salt or another electrolytic solution, but they are in the same solution. So see how usually in a galvanic cell we'll have a little barrier separating these guys, but in this case we don't. Remember, our electrons flow from our anode to our cathode, just like so, because our anode is what's getting oxidized, so electrons are coming off, and those are flowing to the cathode where electrons really want to be gained by the, in this case, the sodium species. So if you'll notice, there's also a source of a direct current right here. That's what powers the oxidation reduction to take place in this cell. So we have the same equation to calculate the voltage. It's the cathode minus the anode for the overall cell potential. But we do have a different reduction and oxidation kind of selection process to know what is the most favorable reaction, what will produce the most volts in this case. So for the reduction half reaction, it will always be the positive ion or the water reduction below. So this means the most positive reduction value. So our E cell for our reduction is going to be the most, let's say, positive, as in plus will equal the most positive for this guy. Yep, and I wrote that down here again. The reduction potential is the most positive, or it could be this guy. And sometimes we'll see in our example down below, actually we'll have to choose between which one we want to choose based on what is the most positive. So then the oxidation will be the negative the most negative E cell for our reduction potential. So it'll be the most negative, and that actually makes sense if you think about it conceptually, because a reduction needs to flip signs for oxidation. Remember, what with galvanic cells, we flip the sign of the cell potential if we were going to be calculating voltage or swapping it from an oxidation potential. So all of our potentials in AP chemistry are given as reduction values, so we will need to switch our E reduction potential sometimes, or it could be this O2 plus 4 H plus 4 electron yields to H2O. So yeah, we'll see in our next example, we kind of just have to compare and contrast. So this is our first example. We have all these half reactions to choose from. We have the two we looked over just a second ago, and we also have the copper and bromine species. It says a direct current is applied to an aqueous copper bromide solution. So first off the bat, I'm just going to label this as an oxidation, so we can kind of get it in our heads. And then this will be the reduction, if we decide to go with these instead of the species that is reacting. So a direct current is applied to an aqueous copper bromide solution. What is a reduction half reaction? Okay, so we need to look for the most positive between the two that it could be. So we know that here our half reaction that we always will have is this H2O plus 2 electrons, and that's pretty negative. And if we write out the half reaction, say the copper bromide, we are going to want to go with this copper because the most positive out of these two choices, the this water getting split apart, or this copper. So we're going to want to go with this copper and choose that for reduction potential because it's the most positive compared to this negative 0.83. So we will say that our reduction half reaction is copper 2 positive, aqueous, plus 2 electrons, yields copper solid, I believe. Okay, and then same deal, we need to find the oxidation half reaction. And so we are either we're gonna find the most negative reduction value or the most positive oxidation value. So if we flip the signs, which I'd rather just find it in the reduction. If you look at our previous slide, it's going to be the most negative one. So we could either choose this 1.23 or this 1.07. So we're going to look for the smaller one, and that's going to be our 1.07. So this will be our oxidation, and remember we need to flip it because we're getting oxidized. So this ion is going to go back to Br2 when we when we take off 2 electrons, it's going to go back to its elemental state. Sorry. Plus 2 electrons. And how I like to remember these half reactions is if our electrons are in the product, we're getting oxidized, which they are in this case, and if they're in our reactant, then they get reduced, like on this side. So left side of the arrow, they're getting reduced. Right side of the arrow, they're going to oxidize. So let's just duplicate this guy down here, bring him down to our example. That's our oxidation half reaction. And the overall reaction, I'm fairly certain you guys know how to do this by now, so we'll skip that just for the sake of time. And let's calculate our E cell real quick just so we know how to do that. Our E cell will equal our E of our cathode minus our E from our anode. And we already know that our oxidation is going to happen at our anode. So we know that this is at our anode and the copper is at the cathode. So we know our copper reduction potential is a positive 0.34. So we're going to have 0.34 come first, and that's going to be in volts, remember. And what I usually do, especially with all these negatives and positives, I'll write the minus, and then in parentheses, we'll just give the oxidation potential, and we don't have to worry about flipping signs or anything, because that's where we can lose easy points on our AP Chemistry exam. So then we said that our bromine was getting oxidized, and so we're going to use this reduction potential and say 1.07 volts. Down here, 1.07 volts. And this will equal 0.34 minus 1.07. It'll equal a negative 0.73 volts. I don't know what's going on with my pencil. Negative 0.73 volts, which equals our overall cell potential, and that's, we say E naught cell, just our overall cell potential for the overall reaction. And if you'll notice, this is a negative, which essentially means that we need to put in 0.73 volts to get this guy started. So if we were ever asked to interpret this voltage, it would mean that it requires 0.73 volts of energy to be put in before any electrolysis of any species will occur. Again, like I said, this is a little different from galvanic cells, but we're still just building on our oxidation and reduction reactions. So if you have any questions in the comments, let me know. Be sure to like and subscribe, and I will see everyone soon.